apply Hess law in calculating the heat of formation using Hess law and heat of combustion data. Now, you may not always be interested in finding out the heat of formation data only. There might be situations that you are dealing with compounds, right, all of which you know the heat of combustion data, right. So, typically as of now, you listen to this, I will write if necessary. We know that for a given reaction, if the heat of formation data of all the participating compounds and products, of heat of formation data of all compounds which are in the products and the reactants, getting a element as the product is very rare. In most of the cases you get products straight away, you get compounds as products, right, but reactants might be elements or compounds, right. So, for any given chemical reaction, if the heat of formation data of all compounds that are involved either in the form of product or maybe also as reactants, if those are known, the heat of the standard heat of reaction at 25 degree centigrade you can find out. And we also discussed about what happens if you have reactants and products at different temperature. You essentially have to consider that the change in enthalpy, right. So, maybe I will just write it down. So, for the sake of completeness, because this I remember I did not write down the expression I just mentioned. So, calculation of heat of reaction for a process in which the reactants and products enter or exit at different temperature than 25 degree centigrade. As of now, we are assuming pressure is constant at 1 atmosphere. So, heat of reaction, right. So, what is the fundamental difference? Heat of reaction at any particular temperature, right, this temperature you need to specify, and the symbol is no longer this 0. This 0 actually implies that your reaction is taking place at 25 degree centigrade and 1 atmosphere. So, this is the standard heat of reaction However, it is possible, as I mentioned in the previous class, it is possible to calculate or have heat of reaction at any temperature, right. So, when you talk about heat of reaction at any temperature, so what exactly do you do? Because the problem is as follows. So, suppose if you have a reaction, right, where let us say A plus B leading to C plus D. Now, if the reaction is taking place at 25 degree centigrade and 1 atmospheric pressure, A, B, C, D can be elements or compounds. So, what I was trying to emphasize that C and D, since they are products of a chemical reaction, in most cases they are compounds. There are certain reactions where elements get generated, for example, synthesis reactions of oxygen, let us say, or other type of elements. So, A, B, C, D can be elements or compounds, whatever. Now, you know that if the heat of reaction, if the reaction is progressing at 25 degree centigrade and 1 atmospheric pressure, the heat of the standard heat of reaction you can straight away find out from the standard heat of formation, the calculating the standard heat of formations, right, which we all know. And amongst A, B, C, D, if you have some elements, that in that case that particular HF0 value will be 0. Now, what is the problem here? What is the problem here? If you want to write an expression similar to this at an elevated temperature. So, hypothetically let us say that, so answer is, can we directly, this is a very simple thing, but I thought I will clarify it. Can we directly write an expression like this to calculate delta H r at any temperature, right? The answer is theoretically yes, provided you know the heat of formation data for all these A, B, C, D, all the participating reactants and products at that temperature. But unfortunately, heat of formation, you typically will not find a table which gives heat of formation at different temperatures. Heat of formation is available only under the standard condition, because that is why it is called the standard heat of formation. So, are you clear? So, even if you write an expression like this and you say that it is HFC plus or heat of formation of the products minus heat of formation, the summation of the heat of formation of the products minus summation of the heat of formation of the reactants. The problem is, it is a very practical problem, and sometimes you actually, instead of building only concepts and talking big jargons, you need to understand the practicality. These datas at that temperature not available. So, what is the way out? The way out is very simple. You essentially need to think that as if your reactants are brought down to a temperature of 25 degree centigrade, the reaction takes place over there, and then the products are heated up back to whatever is the exit temperature. The reactants and the products can be at the same temperature. So, your expression for heat of reaction at any particular temperature now reduces to, so enthalpy of the reactants or the products at 25 degree centigrade for the products minus the enthalpy change. So, this is the enthalpy change actually plus the standard heat of reaction, which you can calculate at 25 degree centigrade. And what are these? How do you calculate these? So, these are very simple actually, that is what we have. So, this is the ith component. So, HIT minus HI at 25 degree centigrade, this is nothing but number of moles present into 25 degree centigrade or to say 298 Kelvin, depending on whether you have absolute temperature or whatever, Cp I dt, right, plus if there are any phase changes. So, if there is some phase change associated, then even this term might get more complicated. So, T to the phase change temperature, let us say the boiling point, right. So, it can be a very simple example. Suppose you have steam entering into a reaction chamber, steam is not being used as a cooling medium or heating medium, but is used as a source of water, and you know the standard heat of reaction, where one of the reactants is water. So, what does it mean? Let us say steam enters the chamber at 150 degree centigrade, and then you have a reaction where water is one of the reactants. So, what does it mean? What you have to do? You have to assume as if this steam, let us say it is at 1 atmospheric pressure, let us complicate the complication associated with pressure. So, you have to assume that this steam is reduced to a temperature from vapor phase to the liquid phase, from vapor phase 150 degree centigrade at vapor phase to liquid phase at 25 degree centigrade. So, what happens to this particular term? You actually have the sensible heat part to be calculated based on the Cp value of steam from 150 degree centigrade to 100 degree centigrade. Then there is a phase change at 100 degree centigrade, and then you have to consider the Cp value or the calculate the sensible heat for liquid water from 100 degree centigrade to 25 degree centigrade. It goes like this. I am not picking up a problem, but it goes like this. So, essentially this is how you calculate the heat of reaction if your reactants and products are at different temperatures, which is not at 25 degree centigrade. I am not talking about the pressure effects right now. So, anyway, this is sort of a side discussion which probably is little bit of leftover from one of our previous classes. So, right now for this lecture we were continuing with the application of Hess law, and essentially we are going to pick up another example, calculation of standard heat of reaction from heat of combustion data. Right. So, this is how it goes, and for this let us pick up one example. So, let us say calculate the heat of reaction, standard heat of reaction, that is why the 0 is there. So, please do understand that you are a knowledgeable class set of people. So, whenever HR 0 is there, it is standard heat of reaction, right. And if it is simply HR, then immediately you must ask for what is the temperature and pressure, because HR 0 is specified at 25 degree centigrade and 1 atmospheric pressure. You might be wondering why I am emphasizing on this. Many people make this mistake in pedagogy, right. So, you should not make. So, calculate HR for the following reaction. And this is beginning of some very interesting discussion. So, which is C2H5OH ethyl alcohol plus CH3COOH, this is acetic acid as you all know. So, this leads to ethyl acetate and water. And what you have, so see, if one is allowed to or told to calculate the heat of reaction for this, if you know the heat of formation of water, ethyl acetate, acetic acid and ethyl alcohol, you can straight away do that. But instead of that, see what is provided to you. What is provided to you is these values. So, these three heat of combustion data are given, along with the heat of formation data of water is also given, and which we calculated, we looked into in the very previous problem. So, I will just pick up the number from there, it is minus 68.317 kilocalorie per gram mole. So, this is how it is. So, how do we go about this whole stuff, right? So, again you can say sort of Hess law comes in our rescue, and so what I will do, I will create some space right here, and all we will make a note here is that HC0 of ETOH acetic acid ethyl acetate and heat of formation of water, all these 4 are known, right, only this much are known, right. So, to calculate the heat of reaction, the standard heat of reaction for this equation, we know that the expression is going to be standard heat of formation for acetic acid plus sorry, it is not acetic acid, ethyl acetate right plus water minus standard heat of formation of ETOH minus standard heat of formation of acetic acid. So, this is the final expression that you will be needing under any circumstances. So, what exactly is the challenge here? Challenge here is heat of combustion data for all these compounds are given. So, now we need to look into the heat of combustion, the combustion reactions for each one of them. So, for example, the combustion reaction for ethyl acetate, for example, C2H5OO CCH3, and this is in the liquid form. If you stoichiometrically write it, you will find that plus 5 O2 leads to 4 CO2 gaseous form plus 4 H2O in the liquid form, right. So, in other words, what we have, the heat of reaction of this particular reaction, which is nothing but the heat of combustion for ethyl acetate, is 4 times heat of formation of CO2 plus 4 times heat of formation of water minus heat of formation of ethyl acetate. Of course, heat of formation of oxygen is going to be 0, we know that. So, from here we actually now get an expression for heat of formation of ethyl acetate, right, which is 4 heat of formation of CO2 plus 4 times heat of formation of H2O minus heat of combustion of ethyl acetate. I hope it is clear to all of you, right. So, what are we doing? We now know in order to calculate the heat of reaction, we actually have to use this expression, right. So, what we are doing is we are looking at the combustion reactions. So, we know the expression of these combustion reactions, right. So, essentially the heat of combustion is nothing but the heat of reaction, and which involves the expression of the heat of combustion now involves, or this heat of combustion now involves the heat of formation of ethyl acetate. So, all we are doing is we are now rearranging the expression in such a way that we now have an equation for heat of formation of ethyl acetate, right, and that we are writing in terms of, we are getting it in terms of heat of formation of carbon dioxide, heat of formation of water and heat of combustion of ethyl acetate. I hope it is clear. So, you can start guessing what next. Yeah, what next is that we need to look into the combustion reaction for C2H5OH, and which turns out to be that if you react 3 O2, right, it will give 2 CO2 and 3 H2O liquid. So, here also the heat of combustion of C2H5OH, right, the heat of combustion of C2H5OH, which is the heat of reaction, will be twice heat of formation of carbon dioxide plus thrice the heat of formation of water, minus oxygen of course gets cancelled away, minus the heat of formation, oxygen is 0, of ETOH. So, from here we will get an expression for heat of formation of ETOH equal to thrice the heat of formation of water plus twice the heat of formation of CO2 minus the heat of combustion of C2H5OH. And similarly, what you can, let me write it, let us not rush. So, the only problem that we will have is we will have to change slide, but we will write this expression. So, the third thing that remains. So, see, we have looked into the combustion reaction of ethyl acetate, we have looked into the combustion reaction of ethyl alcohol. So, next we need to look into the combustion reaction of acetic acid, and which is CH3COOH, and here you actually need, so you have 2 carbons. So, 2 O2 would be good enough, right, because 4 hydrogens, yeah, and this leads to 2 CO2. Only thing I am constrained is a little bit of space, nothing else, and 2 H2O liquid. So, from here one can show, I mean if you want me I will write it, the heat of combustion for acetic acid is twice the heat of formation. I think all of you can understand by now, but it is my duty to write every step when I am building the concept, minus the heat of formation of acetic acid. From here what we get, the heat of formation of acetic acid is twice heat of formation of CO2 plus twice heat of formation of H2O minus heat of combustion of acetic acid. This is what we get, and what is important for us is these 3 expressions, right. So, I will be needing part of this slide again. So, let me do one thing, let me copy it and remove the unnecessary stuff or the stuff that is not required. So, what are the stuff we need? So, we need this expression, right. Next what we need is this, you can consider as the duster work in a blackboard class. Sorry for the little bit of time wastage. Okay. And the third one that we need is this expression. Okay. So, oops, sorry, what we have over here is this ethyl acetate. We have this one also we have. I will just write it in a single sentence, minus heat of combustion for C2H5OH, and the third one that we have is heat of formation out here. So, we are running out of time, so we have to be a little fast. And so, now what we already have is the expressions for the three heat of formations as you would need over here. So, you can just start to write that, and so heat of reaction is heat of formation of ethyl acetate, which is 4 times heat of formation of CO2 plus, you have to be a little bit careful about these heat of formation of carbon dioxide and water, minus heat of combustion of ethyl acetate, right, plus heat of formation of water, which anyway comes from here, right. This will all come with cap except this, minus the heat of formation of ethyl alcohol. So, heat of formation of ethyl alcohol is minus 3 heat of formation of H2O, minus 2 heat of formation of this will all come with caps, sorry about it, CO2, plus the heat of combustion of C2H5OH, minus twice the heat of formation of CO2, minus twice the heat of formation of H2O, plus heat of combustion of acetic acid. And here you need to check what are the stuff you have. So, you essentially have in your equation 4 CO2 plus over here and minus 2 CO2 minus 2 CO2. So, CO2 gets cancelled out, and what you have is 4 H2O, heat of formation of 4 H2O plus 1, that is 5 H2O, and you see that here is 2 H2O over here and 3 H2O over here. So, these actually cancels out, and eventually you get, again if you allow me to write the final expression over here without changing the slide. So, what we get is a very neat and compact expression of heat of reaction is actually the heat of combustion of the acetic acid comes from here, plus heat of combustion of ethyl alcohol comes from here, minus the heat of combustion of ethyl acetate that comes from here, right. So, it is interesting to note actually that here we know that the heat of reaction, right, is of course, you need to do this step to show that the carbon dioxide and water actually cancel out, and you do not need those data. So, that also if the equation is properly balanced, this is going to happen. What is interesting to note is when you are writing the heat of reaction or the standard heat of reaction in terms of the heat of formation data, right, it is actually the summation of the heat of formation of the products minus the heat of formation of the reactants, right. But what you see over here, it is a very interesting relation, and which you have essentially derived right in front of your eyes, that the heat of reaction, the standard heat of reaction turns out to be in the form of the summation of the heat of combustion of the reactants minus the heat of combustion of the products, of course. water is of course not present, right. So, this way there can be n number of such examples, and I would request you to look into Himmelblau's book and practice some. This way with heat of combustion data, you may not waste your time in calculating the heat of formation values. Of course, each of these reactions now can be used to calculate the heat of formation value of these organic compounds, right. You can actually quite easily find out straight away the heat of combustion data, right. So, that is how it goes, and if you just for the sake of curiosity you would like to calculate the heat of reaction over here, it will turn out to be minus, or let me change slide at this point of time. So, heat of reaction minus the standard heat of combustion of ETA, and this gets cancelled out, right. So, here if you plug in these numbers, the data we have in the previous slide, the heat of reaction turns out to be minus 326.70 plus of minus 208.340 minus of minus 538.760 kilocalorie, and it turns out that it is very small, it is 3.20 kilocalorie. So, typically organic compounds have very low heat of combustion, right. So, I think that sort of brings us to the end of this particular class, and in the next class what I am going to pick up, we will continue our discussion on heat of reaction, right, and we will look into some very interesting system, particularly the neutralization reaction between acid and base, reaction between salts, and then look into the thermal effect associated with dilution. Thank you very much.